Okay, so let's. Sorry, can you hear me? Is the microphone on? Hello. Can you hear me? Or not? Okay. So in the last class, what we did was we looked at the Schwartzell solution, right? And remember, the Schwartzell solution is the unique solution with spherical symmetry to the vacuum Einstein's equations. That is, well, in the absence of sources. And one thing that seemed to be a problem with the Schwartzell solution is it seemed to be only valid for r greater than 2gm, okay, or r greater than only 2gm over c square, and this is what we call the Schwartzell radius. Okay, so for something with the mass of the sun, this radius is about 3 kilometers. Now, what we saw in the last class was that if you have particles orbiting whatever is creating this this geometry, you would find that those particles, if they're massive particles, can orbit no closer than 6 times gm. Okay, so they're pretty far away from whatever this is. But of course, there's nothing to stop you from coming close to 2 gm by not orbiting, but let's say by accelerating, okay, by having a rocket ship. If you send your roommate close, your roommate can hover above this 2 gm. Now, what we're going to try to do is we're going to try to use this idea that we saw from Rindler spacetime. So imagine that you had a full Minkowski spacetime, but you were stuck with one of as being one of the Rindler observers. How would you discover the rest of Minkowski spacetime? Well, the answer is simple. You stop accelerating, okay? Or in other words, you follow geodesic, okay? So the geodesics, you can imagine if it's massless particles, they follow null geodesics. If it's massive particles, they follow time-like geodesics. But essentially, besides this Rindler wedge, which is region 1, okay, between this region here, you could also discover region 2, okay, by sending these null geodesics. And as a mathematical step, you could also imagine sending out space-like geodesics to discover the rest of the space. Okay, you can't do this physically. No physical particle can travel in space-like geodesics. But you could imagine mathematically just trying to extend your space or your Rindler patch by following space-like geodesics. And similarly, you can follow past time-like geodesics or past null geodesics to discover this region 3. Okay, so that's what we're going to try to do. So although our Schwartzell coordinates seem to stop at 2 gm over c square, what we'll try to do is we'll try to extend our coordinates by following geodesics. Okay, and we've seen that there's no reason to suspect that anything weird is happening at r is 2 gm over c square. It just appears to be a limitation of our coordinate patch. Okay, that it only covers the regions r greater than 2 gm over c square. So if we can somehow follow geodesics, we've seen that the curvature is non-singular. Okay, at r is equal to 2 gm. So there doesn't seem to be a problem following geodesics, at least beyond this point. Okay, so in that spirit, what we're going to do is let's consider a null geodesic. Okay, and the null geodesic that we'll consider will so this is a path that a light-like particle would take. So light would take this path, and we'll assume one with 0 angular momentum. Okay, that is, it's headed straight for r is equal to 0. Right, we've seen that light would follow some kind of straight line path like this towards r is equal to 0, where theta is pi by 2. Okay, so we fixed that by angular momentum conservation. And since we fixed L is equal to 0, that is, we've also fixed phi to be a constant. Okay, so this is just going to be light heading towards r is equal to 0. Okay, directly in line with this. Okay, now what we'll do is let's consider so the equation for null geodesic. So the equation for null geodesic is it must satisfy this equation, or in other words, it must satisfy ds square is 0. Right? That's the condition for the trajectory to be null. This is the inner product of tangent vectors is 0. Okay. So if I write this out, what I'm basically saying is g mu nu dx nu is 0 along a null geodesic. Okay, and along this null geodesic, theta is 0, theta is fixed, phi is fixed. So dx mu is just this part of ds square. Okay, d theta is 0 because theta is not changing, d phi is 0 because phi is not changing. Okay, so ds square is just this, and this is what you have to equate to 0 along the null geodesic. Okay, so what that gives you is, if you solve this, it gives you dt by dr is equal to plus minus 1 minus 2 gm by r inverse. Okay, that's easy to see from here. Okay, sorry, there's an inverse here. Okay, so dt by dr is equal to 1 minus 2 gm by r inverse. And there's a plus or minus when I take the square root. Okay, the plus or minus simply tells me whether I'm talking about an inward going geodesic, that is R decreasing with time, or is R increasing with time. Okay, so if it's a plus sign, then this is R is increasing with time, so it's an outbound geodesic, so plus is outbound. Okay, whereas the minus sign is an ingoing geodesic, infalling. Okay, geodesic. So these are the two possible geodesics that you can have. Okay, so the only thing that's strange about this is the rate at which you traverse a given R, okay, changes at different R. Okay, so dr, or in other words, dr by dt is not a constant, but rather it changes as 1 over 1 minus 2 gm over R. Okay, plus minus this. And we've seen that before, that this is a way to interpret this as an effective speed of light, right? You can think about the speed of light is changing due to refractive index n, where n is equal to 1 minus 2 gm by r. Okay, so you can think about this as a refractive index which is changing as you're moving closer to r is equal to 0 or r is equal to 2 gm. All right, so now let's look at light cones in this coordinates. Okay, so let's look at dt by dr, and what we're trying to study is, if we look at the t axis here and the r axis here, what we're interested in is, if I'm at a given t and r, what is the path that light will follow? Okay, that's what we call the light cone. Okay, that's the light cone now in general relativity, so now in a curved space-time. So dt by dr will be equal to plus minus 1 minus 2 gm by r, or is equal to c by n, where n is this refractive index. Okay, now you see that as r goes to very large values, okay, the refractive index is nearly 1. Okay, and so the light cone is just your usual 45-degree light cone. Okay, in units where c is equal to 1, it's just your usual 45-degree light cone. But as I get towards smaller values of r, okay, as r gets closer and closer to 2 gm, n goes on increasing now. Okay, as you get closer and closer to r is 2 gm. So as n goes on increasing, okay, the refractive index goes on decreasing. The refractive index goes on increasing. Okay, and the speed sort of slows down, which means the slope of this light curve, now the slope if I look at r as the x-axis, this slope, okay, becomes smaller. Okay, or the slope in t versus r, that slope becomes larger. So this slope becomes larger, it becomes steeper. Okay, and eventually as I get to r is equal to 2 gm, the light cone is almost vertical. Okay, it's like this. So the light cone kind of closes up. Okay, as I get towards r is equal to 2 gm. That closing up of the light cones is a coordinate dependent statement. Okay, because I'm looking at the rate of change of the r coordinate versus the rate of change of the t coordinate as I'm moving, okay, towards r is equal to 2 gm. So this closing up of light cones is definitely a coordinate dependent statement. It's not a coordinate independent statement of the geometry. Okay, so anything that's a coordinate dependent statement is not necessarily an intrinsic property of the geometry. Okay, so you shouldn't worry about this as being some kind of physical effect. This is just a measure of how much r you're covering in a given t. Okay, or how much t it takes to cover a given r. Okay, and basically as you get closer and closer, okay, as you get closer and closer, to cover even a very small amount in r, it takes a very long t, okay, which is a very long coordinate time t. This is something that we've seen in the last class, right? If your roommate is falling in towards the black hole, it would, as they get closer and closer, if they keep sending you signals, those signals would be infinitely spaced apart, right? And it would take you almost till t is equal to infinity to see those signals, okay, as they get close to r is equal to 2 gm. So these are the light cones which are closing up. Okay, we don't know whether these coordinates are valid below 2 gm, but at least till 2 gm, we see these coordinates keep closing up. Okay. Okay, this is very similar to what happens with Rindler coordinates. Okay, in Rindler coordinates, which is just Rindler coordinates in Minkowski spacetime, you have ds square is minus rho square d eta square plus d rho square. Okay, and eta is Rindler time, rho is Rindler your Rindler spatial coordinate. D eta by d rho is plus minus rho. Okay, so again, as rho goes towards 0, okay, as rho goes towards 0, your light cones close up. Okay, as rho goes towards 0, your light cone goes up, d eta by d rho goes to 0. Okay, to cover a very small amount of d rho takes you a very large. Sorry, did I get this right? To cover a very small d rho takes you a very large d eta. Oh, sorry, this is 1 by rho. Okay, if I equate this to 0, what I get is d eta by d rho is 1 by rho. Okay, so as rho goes to 0, if I want to cover a small d rho, it takes me a very large d eta. Okay, now, no, but the amount of time d eta that elapses, okay, that is coordinate time, that's Rindler time, right? We've seen that Rindler time, if I look at Rindler coordinates, okay, this is eta is minus infinity is here, okay, and eta is plus infinity is here. Okay, so no matter how much I go up in Rindler time in eta, I will never cross over into this region. Okay, so that's just a limitation of my coordinate patch. My coordinates are limiting me so that even if I change eta from minus infinity to infinity, at best I will stay in the Rindler patch. Similarly, that's how we should think of what is going on here. Okay, as r goes towards 2gm over c square, at best in our coordinates, t never increases beyond from minus infinity to infinity. Okay, but that doesn't mean that you can't go below r is 0. This is just a coordinate patch. Okay. Okay, so this amount of time dt or d eta that we're looking at is a coordinate dependent time. So what we should really ask is what is the proper time that elapses for a freely falling particle? Because the proper time is the time that would be measured on the clock of a freely falling observer. Okay, so you would need to calculate, let's say you'd have to find, let's say, a time like geodesic, and you'd have to find what is the time that elapses on time like geodesic. So for example, for Rindler time, if you have, let's say, an observer who is freely falling, so freely falling observer is an inertial observer, so let's say they're moving with a speed less than the speed of light. For without loss of generality, let's just assume that they're at 0 speed in this particular Minkowski rest frame, so they're following this kind of trajectory. Okay, so you can see that in Minkowski time, okay, they would cover this would be a finite amount of Minkowski time, which is a finite amount of proper time because this is their rest frame. Okay, so it would take in finite amount of proper time, they would cross the Rindler horizon and they would enter into region 2. Okay, so similarly, in you could calculate a time like geodesic, and you could figure out how much finite proper time it takes, okay, to cross r is equal to 2gm. So your roommate who's falling into this black hole would basically measure a finite time on their clock before they cross the point of r is equal to 2gm. They will not notice anything special in the sense that there's nothing special demarcating that boundary, okay, for them. It's just an artifact of the coordinate choice that you're using. Okay. Okay, so instead of so what we could do is somehow guess the full coordinates, just like somehow if you could guess from Rindler coordinates from eta rho, if you could somehow guess that Tx is really the covering of the full Minkowski space. Okay, you could somehow figure that out, that you could extend coordinates t and x by an appropriate transformation, which means you have to guess, first of all, what is the transformation law between eta rho and Tx. And then you have to realize that even though the Rindler patch is restricted in these coordinates to x greater than 0 and mod x less than mod t, okay, since you're restricted to this Rindler patch, then you realize after making the switch that your metric takes this form, dt square minus dx square. And then there's no problem with extending these coordinates, not just to be in this patch, but to cover, let's say, this unrestricted range of t and x. Okay, so you'd have to make a guess like this. Okay, and it seems kind of out of the blue if you were just restricted to the Rindler patch to make this guess. Okay, because the transformation involves some cosh, hyperbolic, and so on. Okay, so you have to figure out the transformation rule between tx and eta. You have to first guess the transformation. So it would be rho sinh eta rho cos eta. Then you have to realize that, okay, x and t are bounded like this if my rho and eta have some range, and therefore I can now get a metric which is regular, okay, at these boundaries, and therefore t and x can be continued to cover the entire space. Okay, so this is what you would have to do, and in principle you have to do this for the Schwarzschild case. You're restricted to a coordinate patch where you're using r greater than 2gm over c square and t between minus infinity and infinity. What you want to do is guess a coordinate transformation, okay, to some other set of coordinates. So let's call those coordinates capital X, capital T. And you want to guess this set of coordinate transformations, okay, from r t to x comma capital T. And of course, I'm assuming theta phi I'm not changing. Okay, so you want to guess this coordinate transformation. And in somehow the guess is that once you put your metric in these coordinates, then your metric is going to be regular, okay, in the sense that there'll be a dt square, dx square, and then there'll be some coefficients. We don't know what those coefficients are. Okay, but the coefficients will be regular at r is equal to 2gm. Okay, whatever is your point where r is equal to 2gm, these coefficients will not vanish. Okay, so you will not have degeneracy of the metric, and therefore you expect that even though this dictionary is only valid in some restricted range of x, t, theta, phi, you can extend that range of x and t to cover the entire space. Okay, so this is what we would want to do. The only trouble with this entire thing is, how do you make a guess? Okay, how do you make a guess for what is that right coordinate transformation? Okay, so so what we're going to do is, rather than directly write down the answer, what we'll do is we'll try to write down some motivated guesses. Okay, so a series of guesses of a series of coordinate transformations which will get us to the right x and t that we need to in order for this entire story to hold true. Okay, any questions here? Okay, so what is our problem, right? Our problem is that dt by dr is going to infinity, which means to cover a very small r as I get towards 2gm, it takes me infinite amount of coordinate time t. Okay, so what we'd like to do is we'd like to switch our time variable to something that changes more slowly with r, right? So that the hope is that even if I cross r as 2gm, t kind of still does not cross infinity or reach of infinity, and I can still keep going forward in whatever new time coordinate I have. Okay, so the first thing that we want to do is change to a time coordinate that's varying more slowly. Okay, so the way we'll do this is we'll first solve for the radial null curves. That is, we'll solve for the curves which are these null geodesics which are going towards r is equal to 0. So dt is equal to plus minus dr over 1 minus 2gm by r. We'll define dr over 1 minus 2gm by r as plus minus dr star. Okay, where r star is something called a tortoise coordinate. Okay, tortoise coordinate. Why? Because you cover you cover very little r star. Okay, as you get closer and closer towards 2gm compared to how much r you would cover. Okay, so so in these null coordinates. Okay, so now our null geodesics, right? Our null geodesics were the ones for which dt by dr is equal to 1 over 1 minus 2gm by r. Okay, so in other words, in these coordinates, we're saying dt is equal to dr star. Okay, and this can be easily integrated to give you a relationship between r and r star. Okay, so the null geodesics in the t and r star coordinates are very simple. It's t is equal to plus minus r star plus a constant. Okay. Plus is again the outgoing geodesics, minus sign corresponds to infalling geodesics. Okay, so t is r star is outgoing null geodesic, and t is minus r star plus constant is incoming null geodesics. Okay, the constant is of course easy to understand. It's when you start when you are located at a particular r star at some time t. Okay, and by integrating this equation, okay, you can figure out a relationship between r star and r up to a constant, and you choose that constant in such a way that r star is equal to r plus 2gm log r over 2gm minus 1. Okay, this is just the integral of this equation. Okay. what I get by this indefinite integration. Now what you do is, okay, so if I look at r star as a function of r, so what we see is that as at large r, okay, log of r is very slowly changing with r. So at very large values of r star is approximately just r, okay, just scales like r, okay. But as I get towards r is equal to 2gm, okay, as I get close to r is equal to 2gm, this log term becomes important, and if I plug in r is equal to 2gm, this is 0. This is sorry. This is 0. So log of this is minus infinity. Okay, and r is finite. R is 2gm. So at r is equal to 2gm, this becomes minus infinity. Okay, so my tortoise coordinate r star goes from infinity to minus infinity. Okay, rather than r, which just goes from 2gm to infinity. Okay, so after this change of coordinate, r star covers a larger range. Okay, so now we can plug this in, okay, into the metric. Okay, and what we can do is now we can write. Sorry, where did I? Yeah, so we had dt square times 1 minus 2gm by r. Okay, plus now we have dr square over 1 minus 2gm by r. Okay, and what I can do is I can square this and multiply by 1 minus 2gm by r. And dr square over 1 minus 2gm over r square is dr star square. Okay, it's the tortoise coordinate square. Okay, so that gives me a common factor of 1 minus 2gm by r dt square minus dr star square. Okay, plus r square d omega square. Now, this looks a little confusing because you have r and r star, but we have a dictionary which relates r to r star. Okay, which means that you should really regard this metric now as a function of t and r star. And this r is sort of implicitly defined by this equation. There's a one-to-one relationship between r and r star. Okay, but that one-to-one relation is complicated to solve for. It's easy to solve for r star in terms of r, but inverting this, because this is a transcendental equation, right? If you want to invert it, you can't invert it. Okay, but there is the inverse exists. Okay, you just can't write it down in some simple analytic form. Okay, so the inverse exists because you can plot it and you can see that the inverse exists. Okay, this is a one-to-one function, or it's a monotonic function. Okay, so so now this r should be regarded as a function of r star. So if you want to be very pedantic, you can write this as r is a function of r star, r is a function of r star here. Okay, so really this is metric is a function of t, r star, theta, and phi. Okay, and now we can ask in terms of the light cones. Okay, in terms of the light cones, if we look at r star, of course, we can ask what happens to the light cones. And you can see in this, the radial null curves have dt by dr star equal to 0. Okay, that because d omega is anyway 0 because it's radial. Okay, theta is fixed, phi is fixed. So if I want ds square is equal to 0, I just want dt is equal to dr star. Okay, that gives me my radial null curves. So dt by dr is plus minus 1. Sorry. Sorry, yeah, dt is equal to dr. Sorry, that's what I mean. Dt is equal to dr, dr star, okay, or dt by dr is plus minus 1. Okay, again, plus is outgoing, minus is incoming. And now you see that in these coordinates, the light cone doesn't close up. Okay, this is just your 45-degree light cone. Okay, so I cover the same amount of r star at every r star. Okay, for a given dt, I cover the same amount of dr star at every r star. Now, the only price that you have paid by switching to this r star coordinate is that your horizon of this black hole, which is at r is equal to 2gm, that has now moved to r star is minus infinity. Okay, so I have to go all the way to r star is minus infinity, and then I'm near r is equal to 2gm. Okay, so this doesn't quite do what we want to do, but it helps. Okay, in the sense that the light cones are at least not closing up. Okay. By dr star, thank you. Yes, dt by dr star. Okay, now what we'll do is we'll define we'll make a next step. Okay, which is that we'll define a coordinate that's a constant along the geodesic. Okay, that's something that's a constant along the geodesic. So that basically as we go towards r star is minus infinity. Okay, so let's suppose that we have some coordinate called v. Okay, which is constant as we move, okay, this way. Okay, then the hope is that basically this same coordinate, okay, suppose we have two coordinates v and u. Suppose v is constant as we move this way. Okay, then the coordinate u is changing as we move this way. And then the hope is that if u ends up at some particular value, let's say u is u naught here, then if I go beyond u naught, then I will basically extend my geodesic and I will go beyond r is equal to 2gm. Okay, so that's the basic idea. That's what we want to do. We want we now want to switch to a coordinate that is constant as I move along this geodesic. Okay, that is as I move along r star. So what we'll do is we'll define two new coordinates v and u. Okay, v will be t plus r star, u will be t minus r star. Now v is constant along the infalling null geodesics. Okay, because along the infalling null geodesics we've seen yeah, so dt is equal to dr star, sorry, dt is equal to minus dr star. So t is equal to minus r star plus a constant. Okay, so v is a constant basically along an infalling geodesic, and similarly u is a constant along an outgoing geodesic. Okay, outgoing null geodesic. So v is a constant along infalling null geodesics, u is a constant along outgoing null geodesics. And now what we'll do is instead of using t and r star as coordinates, okay, what we'll do is we'll use v and r star as our coordinates. Okay, v is going to be a constant along the geodesic. Okay, and then basically the hope is that as we extend r star, we can cross over into this region with r less than 2gm. So when we use v and r as our coordinates, these are what are called Addington Finkelstein coordinates. Okay, I won't walk through the algebra. It's fairly simple to do. Okay, ds square is minus 1 minus 2gm by r dv square. Okay, all I have to do is convert dt to dv, dv and dr. Okay, so I'll use v and r as the coordinates, and what you get is ds square is minus 1 minus 2gm by r dv square plus dv dr plus dr dv. Now the only reason to split it is just so that you remember when you write down the metric. Okay, when you write down the metric, you'll have a minus 1 minus 2gm by r. Okay, this is the v component, this is the vv component. Then you have the dv dr component, which is 1, and then you have the dr dv component, which is also 1. Okay, because the metric has to be symmetric. Okay, and then I have 0, 0, 0. And then I have my usual r square and r square sine square theta. Okay, this is for my theta component, phi component. 0, sorry, 1, 0, 0, 0, 0, 0, 0, 0. Okay, this is v r theta phi, v r theta phi. Okay, so this is the only reason to write the line element like this. Okay, dr dv is the same as dv dr. But the reason you split it is so that you remember to, when you're writing it as a symmetric matrix, GVR is equal to GRV is equal to 1. Okay, that's what you have to remember. That's the takeaway. It's GVR is the coefficient of dVdr, GRV is the coefficient of dRdV, and both of those have to be the same because your metric is symmetric. So this is the metric. Okay, this is exactly the thing I wrote down here in this VR theta phi basis. So now what you can see is something nice. Okay, now once you switch to this VR coordinates, now if I take the determinant of G, okay, the determinant of G, this term doesn't appear in the determinant, okay, because this gets multiplied by 0 when I expand along the diagonal. So what I'll only get is the product of these two. Okay, so I'll expand, let's say, the determinant along the first row. So I'll get 1 times 1, and there's a minus sign, times 1 times r square sine square theta. So I get minus r to the 4 sine square theta. Okay, when I take the determinant. Now you see that the determinant is non-degenerate as r goes to 2gm. So even if r goes towards 2gm, the eigenvalues of the metric remain non-zero. Okay, which was not the case previously, right? That was exactly the problem that we had previously with the original Schwartzell coordinates, is that in this basis, the metric is diagonal. It's 1 minus 2gm by r, 1 minus 2gm by r, okay, r square sine square theta. And now basically you can see that the metric has 0 eigenvalues as r gets towards 2gm. And that's a problem. That's why the light cones are closing up. Okay. Now you don't have that problem. Okay. So at least now we know that the light cones are not closing up. Okay. It's non-degenerate as R goes towards 2gm. So now the hope is that now, since it's non-degenerate as R goes towards 2gm, we can extend to R less than 2gm. Okay. That is, we can extend our coordinates below this. Okay. So once again, let's try to find the radial null curve. So we'll equate ds squared to 0. So we take this metric. Okay, we set ds squared to 0, d omega is 0 because we're assuming theta is fixed, phi is fixed. So we set this to 0, and so we're solving this equation. 1 minus 2 gm by r dv square times minus sign plus 2 dv dr is 0. Or in other words, we have two solutions. One is dv by dr is 0. That is v is constant, which is the infalling geodesics. Okay, and as we've seen, v is constant is what you expect. Okay, for these infalling geodesics, v is a constant. But for the outgoing geodesics, dv by dr, you have the other solution to this equation, which is dv by dr is equal to 2 over 1 minus 2 gm by r for the outgoing geodesics. Okay, so this describes infalling geodesics in these VR coordinates, and this describes outgoing geodesics in the VR coordinates. So now what we can do is we can look at this, okay, for r greater than 2gm, we can look at these light cones now. Okay, so we look at the v coordinate on the y-axis, the r coordinate on the x-axis, and let's look at the light cones. Okay, so let's look at, so if we look at this part of the light cone, dv by dr is 0, that tells us that one axis of the light cone is always this way. Okay, one axis of the light cone is always this way. Okay, and one of the important points that you'll see is that so if I'm outside, also one axis of the light cone is always this way. Okay, now this is the future of the light cone, that is light going this way. Okay, is going into the future. Okay, this light is going into the future, this is going into the past. Okay, this is going into the past. Okay, or you can think about, if I go along this way, it's coming from the past. Okay, there are two parts of the light cone, right? There's the future part and there's the past of the light cone. Okay, and now the other part of the light cone has a slope which is 2 over 1 minus 2 gm by r. Okay, so what happens to the slope? Well, as r becomes very large, okay, this slope is 2. Okay, so that slope is basically 2. This angle is theta and tan theta is 2. But as r gets closer to 2 gm, okay, this slope goes to infinity. Okay, which means tan theta is infinity, or theta is pi by 2. Okay, so that means this, the other arm of the light cone at r is equal to 2 gm looks like this. Okay, so the light cone is sort of tilting. Okay, so I start out with a very large slope like this. Okay, and then the light cone starts tilting. Okay, so finally at r is equal to 2 gm, it's tilted like this. Okay, where the future is directed this way and the past is directed this way. And now let me just imagine that I can extend my coordinates r beyond 2 gm. Okay, that is, I can go to values smaller than 2 gm. And what you would find is now that this light cone tilts even more. Okay, it tilts like this. Okay, so the light cones in this coordinates, the VR coordinates, do not close, but rather they're tilting. Okay, as I get towards r is equal to 2 gm. And v is equal to constant describes a null geodesic. Okay, so this entire line v is equal to constant is a null geodesic. Okay, so this is, I'm actually following a null geodesic by staying on this line as I just change my r coordinate. Okay, as I just change my r coordinate, I'm following, okay, a null geodesic. And this is exactly the hope, right? That if the metric is not irregular or non-degenerate at r is equal to 2 gm, I can now extend my coordinates beyond r is equal to 2 gm. Okay, and I can enter this interior region. Okay, and if we follow the geodesic inside this region, r is less than 2 gm, then you see that the light cones point inwards. Okay, which means the future is that you will always, okay, go towards r is equal to 0. Okay, once you cross into this region, the future is necessarily that you go towards r is equal to 0, never coming out. Okay, that's why this is a black hole, in that you can never come out. The future light cones, okay, are always directed towards r is equal to 0. which means if you're just sitting around and waiting, that means you're headed towards r is equal to 0. Okay, you can't do anything about it. Okay, you're always going to head towards the coordinate r is equal to 0. Okay, because r is equal to 0 really is now like your time. Okay, you can't stop the flow of time. Okay, you can't stop yourself from heading towards the future. Okay, so similarly in this case you can't stop yourself from going towards the future, and the future is telling you that you have to head towards r is equal to 0. Okay, there is no choice. Okay, so no object can escape out of the region r less than 2 gm, because the light cones of any object, that is the future of any massive particle or even massless particle, is restricted to within the light cone. Massless particles of course have to move exactly on the light cone. Massive particles can move within the light cone, but which means that within the future any massive particle can only move like this. Okay, they can only move like this. That means they're always headed towards r is equal to 0. Okay, and since nothing can escape, okay, nothing can, once you cross r is equal to 2 gm, there's no way to head back out. Okay, not even light can escape this region, so it's called a black hole. Okay, for obvious reasons, because even light can't escape. So, and this surface r is equal to 2 gm is a point of no return. Okay, once you enter that, you can't come out. Okay, it doesn't matter what you try to do, you can't come out. And this is called an event horizon. Okay, so once a particle dips below this point, okay, so once your roommate crossed this r is equal to 2 gm, they can never get out. Okay, they're stuck. Okay, and they're going to head towards r is equal to 0. That's their future. Okay. The other important point is that r is equal to 2 gm, okay, actually defines a null surface. Okay, not a spatial surface. Okay, so it's actually spanned by null geodesics rather than usual space-like surfaces, which are spanned by time-like geodesics. Okay, so let me explain what that means. So if you think about a usual surface in x and t, so let's imagine that you had a region of space, okay, where r is equal to constant. This is in Minkowski spacetime. Okay, and let's imagine that we're just doing this in 2 plus 1 dimensions. So you have x and y. Okay, this is r is equal to constant. R is equal to constant in as time changes. Okay, if r is constant, this region, okay, okay, or this line, this line, this line, this line, these are all time-like geodesics. Okay, these are all time-like geodesics. So the entire surface, the surface of the cylinder, is spanned by time-like geodesics. Okay, that's usually what we would assume when you say r is equal to constant. Is you're thinking about a surface that is space-like. Okay, that is, if I want to get from one point to another at the same time, okay, then I have to follow a space-like geodesic. Okay, or I can think about this with the vertical lines as I'm changing time as a surface which is spanned by time-like geodesics. Okay, but the surface that we are considering, which has coordinates r is equal to 2 gm, this surface is actually a null surface. Why is it a null surface? Well, if I look at r is equal to 2 gm, okay, where did we go? Yeah, r is equal to 2 gm is this point. Okay, the light cone actually lies, okay, along this direction, okay, of constant r. Okay, so the one arm of the light cone at this value of r, okay, is always along the r direction. Is along the v direction. Okay, r is equal to 2 gm is v is changing, but r is fixed. Okay, so you're moving along this direction, and this direction is along one arm of a light cone. Okay, so it's really spanned by a null geodesic. Okay, so this surface is not a space-like surface. Okay, it's a null surface. Okay, that's a rather really important point. This horizon is a null surface. It's very similar to in Rindler coordinates. Okay, your Rindler horizon, which is this, is a null surface. Okay, it's spanned by a light ray. Okay, or a null geodesic. Okay, so the point is, what we call a black hole is a region of space-time, okay, that is separated from infinity, that is asymptotic Minkowski observers, let's say, by a horizon. And this horizon, or this event horizon at r is 2 gm, is a global property of the space-time. That means it's a property of the full space-time. Okay, once you give me the metric on the space-time, does this full space-time have a metric or not? That I have to look at the full space-time to decide this. Okay, and it's not just a property of this region. Okay, it's not just a property of a point over here. It's really a property of the full space-time. Okay, that you have such an event horizon. Okay. All right. Now that you've followed these future-directed paths, okay, and you found that you can cross the event horizon, let's explore. So we said that if you want, for example, in the Rindler case, we said that you could look at future null geodesics, but you could also look at past null geodesics. Okay, and we saw in the Rindler case that future null geodesics take you somewhere into a different region of space-time. Past null geodesics can take you into a different region of space-time. So similarly, in the Schwartzell case, let's try to follow now, instead of following a future-directed null geodesic, let's follow a past-directed null geodesic. Okay, so let's look at now the u coordinate. So u is equal to t minus r star. Okay, this is a radially outward coordinate. Okay, or u is constant along a radially outward geodesic. Okay, so radially outward means in terms of r, if I start at r is equal to 2 gm, okay, I'm now going towards larger r. Okay, for u is equal to constant. Okay, so u is constant means I'm going towards larger values of r as t is increasing. Okay, so now what we'll do is, but what this means is that if we follow this back to small values of time, then again we're going to cross this horizon, but now we're crossing this horizon into the past. Okay, not into the future. Okay, so this previous horizon that we looked at, which was the black hole horizon, when we switched to this v and r coordinates, was we crossed it into the future. Okay, so the future of any null geodesic where you start outside is that you will eventually end up. Okay, and if I just follow the null geodesic, then I directly follow this arm of each light cone, I end up directly inside the horizon. Okay, but now what we're saying is we're going to follow a null geodesic, and we're going to follow a null geodesic into the past. And as we follow it into the past, that is as t goes to minus infinity, we'll follow it again crossing the horizon. But now we'll end up in a different region of space-time. We're not going to end up inside the black hole. The black hole is when you follow it into the future and you cross the event horizon. Now when we follow into the past, we will end up in a different region of space-time. Okay, what is this region of space-time? Let's find out. Okay, so let's take u is equal to constant. Okay, this is some outgoing geodesic, and let's use the coordinates u and r instead of v and r. Okay, so we'll use the outgoing geodesic coordinates. So in these coordinates, ds square, again, you can show this, I'm not going to work through the algebra, is minus 1 minus 2 gm by r du square minus du dr plus dr du plus r square d omega square. Okay, what we saw before for constant v, okay, r star decreased and t increased. So v was equal to t plus r star, okay, and u is equal to t minus r star. And if I want to maintain v constant, we saw that if you could either decrease r star, okay, or increase t. Okay, and as you follow the null geodesic, basically you're doing both. Okay, you're decreasing r star and you're increasing t. You're going forwards in time and you're falling towards the horizon. Now, if you want to maintain u is constant, okay, we will decrease r star as time passes. Okay, so as t decreases, r star will decrease. Okay, and that will maintain u is constant. Okay, so if we use u and r star, we can explore a different region of the space-time. So now, once again, you can draw the light cones. Okay, that in this u and r coordinates. Okay, so you can draw the u is constant. Sorry, this is the u axis. This is the r axis. And if you draw the light cones, okay, the light cones look like this. Okay, so this is the past light cone. This is the future light cone. Okay, one axis is again along the direction of increasing r. Okay, the other axis is sort of tilting now as I come out of the, if I cross the r is equal to 2 gm, these light cones sort of tilt this way. Okay, one axis is always this way, the other axis tilts. Okay, but now you see a very interesting thing. The past of the light cone is at r is equal to 2 gm. The future is always directed towards larger values of r. Okay, and at the critical value, okay, of r is equal to 2 gm, the light cone, basically here, this arm of the light cone is vertical. Okay, and beyond this arm of the light cone is in this form. Okay, so what this means now is if I'm inside, okay, once I cross, once I'm inside, the future always ensures that I will cross r is equal to 2 gm. Okay, I cannot stay inside this region. I will always come out of this region. Okay, so in the future of any light cone which is inside r is equal to 2 gm, I will always go forwards. Okay, I will always go towards larger values of r. Okay, I cannot stay. So in order for me to stay at smaller values of r, what I would have needed is a light cone that looks like this. That way I can, move towards smaller values of r. Okay, but now I can't do that. I always have to keep moving forwards because the flow of time is basically making me move towards larger values of r. Okay, so now what is going to happen is that once I cross the horizon like this into the past, what I find is that things that were inside the horizon now have to come out. They can't stay inside. Okay, they're almost forced out. So this is the opposite of a black hole. Okay, it's what we call a white hole. So if you follow u is constant into the past behind this horizon, you get a different region of space-time for r less than 2 gm. Okay, this is different from the region that we found for the black hole, which is where we followed for v is equal to constant. And in this region that we just found, okay, particles must leave from this region. They can't stay in this region. And once they cross r is 2 gm, they cannot re-enter. Okay, they can't go back into that region. So this region is called a white hole. Okay, so we've seen something interesting, right? If you follow null geodesics into the future, you enter a black hole. If in radially inward null geodesics, you enter a black hole. If you follow radial null geodesics into the past, okay, you see that you came out of a white hole. Okay, what you'd like to do is have some kind of coordinates where you're not looking at one part of the space-time. We don't just want to be looking at the black hole or the white hole. Both of these are present on our manifold. Okay, how do we see the full manifold? What coordinates can we choose so that we can see all of this? Okay, and of course we'd like to see also if there's anything connected by space-like geodesics, we'd like to see that as well. Okay, so one guess for how we could see the full space-time is that we could use maybe both the u and the v coordinates. Okay, let's use both the u and the v coordinates and try to see the full space-time. Okay, this is actually not going to be enough, but it's one step towards actually seeing the full space-time. Okay. Okay, so right. Okay, so let me just write the answer here. Okay, so when you switch to, so from now tr, okay, you switch to tr star, and then you switch further to u and v. Okay, where u is t minus r star and v is t plus r star. Okay, where r star was your tortoise coordinate. And then what you would find is that the metric is in this form. Okay, you have dv du, du dv, and then you have this minus half 1 minus 2 gm by r plus r squared d omega squared. Okay, I'm not working through the algebra. I mean, these are simple steps to work out. Now, t is u plus v by 2. Okay, that you can see from here. T is u plus v by 2, and r star is v minus u by 2. And r star in terms of r is r plus 2 gm log of r by 2 gm minus 1. Okay, so this is the dictionary that relates the original TR coordinates to the new UV coordinates. Okay, and basically the idea is that we want to extend the UV coordinates beyond just the patch in which the TR coordinates are valid. Okay. Now for 2 gm less than r less than infinity and t between minus infinity to infinity, r star we've seen goes between minus infinity and infinity. Okay. So v goes between minus infinity and infinity, and u goes between minus infinity and infinity. But there's a restriction, okay, on this coordinate patch on uv. Sorry, there's no restriction yet. Okay, so u and v still are minus infinity to infinity, but this basically covers the original coordinate patch. Okay, it doesn't really extend below R is 2GM. Okay, so this is still a bit of a problem because it's like if we transformed our coordinates, okay, if we transformed our Rindler coordinates, which were eta rho, to some other coordinates uv, but the uv, when I take their full range from minus infinity to infinity, if they still cover this range, it doesn't quite do me as much good because I don't know how to extend these coordinates into this other region. Okay, so the first thing that we'll do is we see that r is equal to 2gm. Okay, in these coordinates corresponds to r star is minus infinity. Okay, which can either be thought of as the point where v is minus infinity or the point where u is plus infinity. Okay, so the point r is equal to 2gm, that is the horizon of the black hole or the white hole, is the point where either v is minus infinity or where u is plus infinity. Okay, so the first thing that we'll do is we know that we want to cross this horizon, so let's bring in that horizon from an infinite coordinate to a finite coordinate. Okay, so what we'll do is we'll make this redefinition. So we'll define v prime is exponential of v by 4gm. Okay, so what this does is it now pulls in the infinite coordinate, v is minus infinity, which is the horizon. It now pulls it into v prime is 0. Okay, it now pulls in v is infinity to v prime is 0. Okay, so that's the advantage of this coordinate transformation. And similarly, what we'll do for u is we'll bring the point with u is plus infinity and bring it to some coordinate u prime, which is 0. Okay, so u prime is defined as minus e to the minus u over 4gm, where u prime now goes from minus infinity to 0. Okay, and now the strategy will be that our entire region with r greater than 2gm, okay, in the u prime v prime coordinates is only covered by u prime between minus infinity to 0 and v prime between 0 to infinity. And now the hope is that basically we can extend our coordinates by now taking u prime from minus infinity to infinity, v prime from minus infinity to infinity, and this will basically explore the whole space-time. Okay, so first let's just use this dictionary, which is valid in the coordinate patch that we're using with r greater than 2gm. Okay, and we can write down basically the transformation between v prime u prime and the original rt coordinates. Okay, so you just have to plug in for v and u. Okay, where v and u are defined in terms of r and t using these equations. Again, it's simple algebra, so I won't do it. Okay, so you get v prime is equal to this r over 2gm minus 1 to the half e raised to r plus t over 4gm, and u prime is minus r over 2gm minus 1 to the half e raised to r minus t over 4gm. Okay, and you see that this dictionary is obviously only valid for r greater than 2gm. Right, this dictionary doesn't make sense for r less than 2gm because then v prime would be imaginary. Our coordinates by default are real. Okay, so this dictionary is only valid in the patch where r is greater than 2gm. Okay, but once we define the coordinates v prime and u prime, we'll now evaluate the metric. We'll show that the metric is non-singular, and then we'll extend our coordinates v prime u prime to cover the entire space. Okay, so in the v prime u prime coordinates, we can write down now using this dictionary. We can write down dv prime, okay, in terms of dv, du prime in terms of du, and then we can write du dv in terms of du prime dv prime. It's something messy, but it basically involves this exponential and so on. So at the end, when you write down the metric in the u prime v prime coordinates, okay, what you have is ds square is equal to minus 16 g cube m cube by r e to the minus r by 2gm du prime dv prime dv prime du prime. Okay, and this r has to be translated back to u prime v prime. But that translation is given through an implicit equation, which you can't solve again. But there's some relationship, okay, which is u prime v prime is 1 minus r by 2gm times e to the r by 2gm. Okay, so u prime v prime are restricted to satisfy this condition. Or you can think about it as I can invert this relation and find r for a given u prime and v prime. So r really over here I should think of as a function of u prime and v prime. Okay, what is that function? Well, it's hard to do because you can't invert this. This is a transcendental function. Okay, so okay, now the thing is, if you have r greater than 0, okay, if you have r greater than 0, sorry, if you have r greater than 2gm, okay, if you have r greater than 2gm, this is negative. Okay, so in other words, you have u prime v prime is negative. So u prime v prime is negative means that either u prime is negative or v prime is negative, but not both simultaneously. So that is v prime covers this range, right, which we've already seen before. It covers the range 0 to infinity, and u prime covers the range 0 to sorry. Yeah, minus infinity. So actually, the dictionary that we used only covers, strictly speaking, this range. Okay, where v prime went from minus infinity to 0, and u prime. Sorry, did I get it wrong? U prime was minus infinity to 0, and v prime was 0 to infinity. So our coordinates actually cover only this patch. Okay, in the region where the dictionary works between RT and u prime v prime. So v prime goes between 0 to infinity, and u prime goes between minus infinity and 0. Okay, this is the u prime. Okay, now the point is that r is equal to 2gm does not lead to any problem. Okay, now r is equal to 2gm basically means that you will cross over. If I cross r is equal to 2gm, the sign of u prime v prime changes. Okay, u prime v prime becomes greater than 0. So crossing the horizon basically means that I would cross over either into this region or into this region. Okay, so what we're going to do is effectively now we see that there is no problem with crossing over into those regions because this coefficient, right, is non-singular at or non-degenerate, doesn't become 0 at r is equal to 2gm. So the metric is non-degenerate, okay, at r is equal to 2gm. So in the u prime v prime coordinates, you can perfectly well cross over this way, and you can perfectly well cross over this way, okay, which is basically crossing the horizon. Okay, so you can cross the horizon either this way, or you can cross the horizon this way. Okay, so crossing r is equal to 2gm does not lead to any degeneracies. So now instead of restricting our u prime v prime to only this region, we will now just make a simple guess that u prime v prime can be extended over their full range. Okay, u prime can be from minus infinity to infinity, v prime can be from minus infinity to infinity. Let's just accept whatever metric we get out of it. Okay, because that is a perfectly non-degenerate metric. Okay, and the other thing is, okay, so this is what we'll do, and then what we expect is that now we're going to cover the region inside those horizons. So we'll cover the region with the black hole, the region with the white hole, and maybe some other regions of space-time we'll discover as well. Okay, now there's only one more thing left to do, because if you look at this metric, we're not so comfortable working with things where you have a cross term like this, right? We'd rather put it in a form where instead of having something like du dv prime, we'd rather write it as dx prime or dt prime square minus dx square. Okay, something like that. Okay, so we'll just make one final trick, which is that we'll define a t coordinate like this as half v prime plus u prime, and r coordinate as half v prime minus u prime. Now it's quite easy to see that if you write minus dt square plus dr square, this is minus dv prime times du prime. Okay, so so now you can write down, of course, the final dictionary, because you know the dictionary from tr to u prime v prime, and now you know this conversion to capital T capital R also. Okay, and capital T capital R. Okay, you can write down the dictionary. It looks like this. It's just this. So it's just defined in terms of sine hyperbolics and cos hyperbolic. Okay. Yeah. Now in the original coordinate patch in which TR were valid, okay, in which you had restricted u prime v prime into this region, okay, where you had not crossed the horizon, that is, if you are in R greater than 2gm. Okay, in that region, you are restricted to having R between capital R between 0 to infinity. Okay, this capital R is only going from 0 to infinity. Okay, and the other restriction is, if you look at this, t square minus r square, or minus t square plus r square is r over 2gm minus 1, e raised to r over 2gm. For r greater than 2gm, this is positive, which means that r is greater than mod t. So you're also restricting to the region r or mod t is less than r. Sorry, did I get that right? Yeah, r is greater than mod t. Okay, so you're restricted to this coordinate patch if you're restricting your dictionary. Of course, if you once you extend your uv coordinates, okay, to cover the full range, or your u prime v prime to cover the full range, then r and t will also cover the full range. Okay, that is minus infinity less than t less than infinity, and r between minus infinity and infinity. Okay, so let's write out the metric in these capital R, capital T coordinates. What you will find is ds square is 32 g cube m cube by r, e to the minus r by 2 gm minus dt square plus dr square plus r square d omega square. And the relationship between small r and capital T, capital R is this. Okay, so small r, implicitly I should imagine inverting this equation and writing small r in terms of capital T, capital R. Okay, and plugging it in here. Okay. Once I plug it in, then I have an equation for the metric expressed purely in terms of tr theta phi. And now if I extend my tr theta phi to cover the full range of coordinates, this I claim is now the full space-time. Okay, this is the full space-time, which includes the black hole and white hole and everything else. Okay. So these coordinates, this capital T, capital R, theta phi, these are called Kruskal-Zacharias coordinates. Okay, Kruskal-Zacharias coordinates. Just named after the people who invented this coordinate transformation. So you can see that this is quite a messy coordinate transformation, right? There's almost no way you'd guess this as the correct coordinate transformation. Okay, and therefore there's no way to guess that this is the extension. This, it turns out, is the maximal possible extension that you can have for the Schwarzschild metric that we wrote down. Okay. Okay, now in these Kruskal-Zacharias coordinates, okay, what we'll do is let's try to study the full space-time. Now that this will cover the full space-time, let's try to understand what this full space-time looks like. So if we take radial null curves, okay, these radial null curves are ones which will now have just ds square is 0, or if theta is constant, phi is constant. Those are just curves where dt is equal to dr. Okay, or t is equal to plus minus r plus a constant. Okay, so that means in Kruskal-Zacharias coordinates, okay, if I plot t and r, okay, null geodesics are basically 45-degree lines. Okay, either this or this. Okay, so that's one advantage of using Kruskal-Zacharias coordinates, is that null geodesics are always going to be 45-degree lines, just like Minkowski space-time. Okay. The other thing is, what is the location of the event horizon? The location of the event horizon is at r is equal to 2 gm. Sorry, something went wrong with the meeting. Samay, can you hear me? Anyone online? Can you hear me? We got disconnected from.
Yes, sir.
Okay.
Yes,
Okay, so now let's ask, where is the event horizon? So the event horizon was at r is equal to 2 gm. Okay, and the event horizon, if you look at this coordinate transformation, r is equal to 2 gm is where t is equal to mod r. Okay, so the event horizon is at t is equal to plus minus r, which means that now in my tr coordinates, the event horizon is here. Okay, so crossing into this region by a null geodesic would be crossing the point of r is equal to 2 gm. Okay, so that would be crossing into into the black hole or the white hole. Okay, it's a future directed null geodesic, so it will cross into the black hole. If it's a past directed null geodesic, it will cross into the white hole. So this is the black hole region. This is the white hole region. Okay. And sorry, the other point is that I'm of course suppressing the theta phi coordinates. So in Kruskal-Zacharias coordinates, if I think about tr, if I take any point here, you should imagine that there's a 2 sphere in theta and phi associated with that point. Okay, so I'm only showing the t and r coordinates. There's also a theta and a phi coordinate. Okay. Okay, now I could also look at, so if this is capital T and this is capital R, I am also interested in terms of my original R, okay, R is equal to constant. What do those surfaces look like? Okay, what does R is equal to constant look like in capital R, capital T and capital R? Well, again, we can use this dictionary. Okay, it tells us that if R is a constant, minus T square plus R square is a constant, which is a hyperbola. Okay, which is a hyperbola. So so what we get is R is equal to constant would be something like this. It would be some kind of hyperbola like this. This is R as a constant. The limiting hyperbola would be R is equal to 2gm, which would be this. Okay. And also we could ask, okay, for T is equal to constant, what do we get? Well, you can again use the dictionary, and T by R is equal to tan hyperbolic T by 4gm. Okay, which means that T is constant. Okay, describes T by R as a constant, which is a straight line through the origin. Okay, these are lines where T is constant. T is T1, T is T2, and so on. Okay, so this is very nice, right? It's starting to look exactly like Rindler coordinates, okay, in some sense. Okay, this, like, we had eta is constant along these straight lines, and we had rho is constant along these hyperbolas, right, for Rindler observers. Okay, but the important point is, you see that as T goes to plus minus infinity, T by R approaches R is equal to 2gm, okay, or R is equal to minus 2gm. Sorry, T by R approaches plus minus 1, okay, which is basically approaching this horizon here, or approaching the horizon here. So if T is equal to infinity, I approach this horizon. If T is equal to minus infinity, I approach this horizon. Again, this is exactly like what we've seen in the Rindler case, right? As you go to minus infinity in Rindler time, you approach the horizons. You either approach this horizon or you approach this future horizon. Okay, and it's just a limitation of the fact that your T coordinate or your eta coordinate in Rindler coordinates doesn't cover the full space time. Okay, but if I extend to this capital T and capital R coordinates, this capital T and capital R coordinates cover the full space time. Okay, these are like your Tx coordinates of original Minkowski space time, as opposed to your Rindler coordinates. Okay, for R less than 2gm, your original R comma T coordinates are no good. Okay, they don't work there. But capital T can be used because we now extended beyond the horizon. So our full spacetime actually looks something like this. Okay, so let me explain this picture in some detail. Okay, so here I've drawn these two yellow lines. Okay, this one and this one. These are the lines T is equal to plus minus R. These describe the horizon. Okay, small r is equal to 2gm. Okay, our original dictionary is valid only here. Okay, our original dictionary between R, T and capital T, capital R is only valid in this region. It's just like the Rindler patch. Okay, it's only valid in this region. So this is us. Okay, so I've written us over here. Okay, so we exist in this region. In our past, if I take a line going into the past, I enter a white hole. Okay, how far does this white hole extend in the capital T, capital R coordinates? Well, it turns out you can't actually extend capital T, capital R all the way to cover the full space time. Okay, you can't extend capital T, capital R to cover this full region. Okay, it turns out that there's a restriction that they still must satisfy, which comes from here. Okay, which is that that even if I go to R is equal to 0, okay, if I go to R is equal to 0, then I end up at a point where minus T square plus R square is equal to what do I get? Minus 1. Okay, so if I stop at R is equal to 0, okay, R is equal to 0 is a point where I have to stop, because even in this capital T, capital R coordinates, something singular is happening here at R is equal to 0. In fact, if you compute the Riemann curvature tensor, you will find that your Riemann curvature tensor goes like 1 by R, and at R goes to 0, that's 1 by R to some power, and at R goes to 0, it basically becomes infinite. Okay, so there is a problem with going towards, I mean, I can't extend further. I can't cover the full space of minus infinity in T and R. I can at most go to the point where minus T square plus R square is minus 1. Okay, So what that means is this describes a hyperbola, okay, and this is a hyperbola which is so if I write it like this, t square minus r square is equal to 1. Okay, so this is a hyperbola passing through the point t comma r is 1 comma 0. Okay, so that's over here. I've shown this hyperbola over here. So this is the point 1 comma 0. Okay, and this is that hyperbola. This is one arm of the hyperbola, and this is the other arm of that hyperbola. Okay, in the original coordinates, this would be like r is equal to 0. Of course, the original coordinates don't work below r is 2 gm. Okay, but this is the point where r is equal to 0, or basically where the curvature blows up. Okay, so this is a singularity. This is a genuine singularity. Okay, the manifold has infinite curvature. Okay, in this region of space-time. Okay, so you can't really cross this hyperbola. Okay, the interior over here, okay, is the black hole. The interior is the region between this singularity at r is equal to 0 and this light points. Okay, this region. This is the black hole. Similarly, the opposite region here is the white hole. Okay, now you're left with something completely new, which is this region over here. Okay, this region is completely disconnected from us. No signal from there will ever reach us. It'll go into the black hole, but anything that enters the black hole can never come out and reach us. Okay, or things from the white hole can enter this region. Okay, but those things can never reach us. So this is a parallel universe. Okay, it's another universe in the sense that if you were living in this universe, you could not tell. Okay, you would think of this as us, and this is your parallel universe. Okay, so the laws of physics here are the same as the laws of physics here. It's just two causally disconnected regions that can never influence each other. Okay, so this is a parallel universe that exists independently of us. How do you meet someone from there? Well, you and your roommate are here. You send your roommate into the black hole. Okay, and your evil twin and your roommate's evil twin here, they send the roommate's evil twin into the black hole. Oops. Okay, and so your roommate and the roommate prime, they can meet inside the black hole and exchange information about the worlds that they came from. Okay, but anyone outside the black holes will never know of the existence of this parallel universe. Okay, okay, and they can briefly shake hands before they hit the singularity. Okay, okay, so in a simplified picture, okay, this is TR. These are your singularities. Okay, this is your singularity. The R is equal to 0 singularity. Okay, the yellow regions are the R is equal to 2 GM regions, which really now we know are null hypersurfaces. Okay, these are not time-like hypersurfaces. These are null hypersurfaces. Region 1 is us. Region 2 is the black hole. Okay, region 3 is the white hole. Region 4 is the parallel universe. Okay, from which we can't get any signals. Okay, so this parallel universe, okay, actually the geometry can be thought of in a very interesting way. Okay, you can think of this geometry as something called a wormhole. Okay, so what is this wormhole? Well, let's imagine a space-like surface at some fixed value of t. So let's imagine that you are at some fixed value of t. So this is some space-like surface. So let me draw it like this. This is some space-like surface. Okay, I'm drawing it in one angular coordinate also. So this is, let's say, r, and this is, as I change theta, okay, I'm going around this way. Okay, but this is at a fixed value of t. Okay, so I'm fixing t, that is I'm on this slice. The parallel universe is here. This is their t and this is their r. Okay, their r values are negative. Okay, and they live in this parallel universe. Now what happens is, as time passes, okay, we are separated from each other by this sort of white hole. Okay, that is, there's a region of r values. Okay, where there's sort of a defect that develops in the middle. Okay, and eventually what happens is, at some point, okay, so sorry, so let me just say, in terms of r, you can think of a white hole horizon sort of existing here. Okay, and a white hole horizon existing here as well. Okay, and now what is going to happen is, as you cross some critical time, okay, as you cross some critical time, these regions connect with each other. Okay, these regions connect with each other inside the white hole. So inside the white hole, okay, you have a connection between these two regions. So inside the white hole can be thought of as some kind of connection like this, okay, which is inside the white hole. And then as I cross t is equal to 0, this region is now a black hole. Okay, that is, things which fall inside will never come out. Okay, and eventually once I cross again a critical value here, okay, then the black hole pinches this sort of wormhole pinches off. Okay, and again I end up with something which is now a black hole. Okay, a black hole here and a black hole here. So very briefly, there was a region between these white holes or black holes that opened up, okay, which was a bridge between these two different parallel universes. Okay, so that bridge is called a wormhole. But the problem with this wormhole is that you can never cross the wormhole. You can never send a time-like observer who will come out from region 1 and end up in region 4. Okay, they will always end up at the singularity inside the black hole. Okay, in their future, they will never actually cross. So this is called a non-traversable wormhole. I don't know if I wrote it somewhere here. Yeah, so oops. Yeah, this is a non-traversable wormhole. You can't cross this wormhole. Okay, so you can never get from region 1 to region 4 as a massive observer. Okay, so it's quite rich. Okay, so you see that we started with the Schwartzell solution, which was the only solution which was spherically symmetric. Okay, and now what we found is that if I take and the solution only seemed to be valid for r greater than 2gm, but we saw that this is really a coordinate artifact. Okay, so we switched our coordinates to this capital R capital T coordinates, and now we see that we discover quite a rich space-time. Okay, this rich space-time has a white hole region which can be regarded as sort of the beginning of our universe, a singularity from which stuff comes out and fills up our universe. Okay, and then there's a future into, if you fall into this black hole, then you will end up so kind of hitting a singularity. But there's also a future where you don't hit the black hole, right? Where you just travel off to infinity and don't enter the black hole, right? And so that's us, right? Let's say if we don't encounter a black hole, you just live your life peacefully far into the future. Okay. And then there is also this possibility of these parallel universes, which maybe if you discover some kind of different solution, not this solution, you could have a wormhole which connects you to such a parallel universe, okay, where you can actually travel, okay, to a completely disjoint region of space-time for a brief amount, for a brief period in your universe's history. A region of space opens up where you can cross into that other parallel universe. Okay, that would be a traversable wormhole. It's still an open question whether traversable wormholes actually exist as valid solutions in GR. Okay. One other thing I'll just point out is that in region 1, we use the RT coordinates and we sort of had this dictionary. Okay. But what you can do is actually in this region 2, 3, and 4, we said that the small r, small t coordinates are not valid. But really what we can do is we can still use the small r, small t coordinates even in region 3 and 4, 2, 3, and 4. Okay, that is these extra regions. But these R and T are now restricted only to different coordinate patches. Okay, it's like instead of using the coordinate patch eta rho to describe hyperbolas in this region, you use eta rho to describe hyperbolas in this region. Okay, you're using the same symbol for things in this region versus things in this region. Okay, but there's no dictionary of overlap between these two regions, so it's okay to do this. Okay, as long as you're clear which region you're talking about, you can use describe hyperbolas here by using eta rho, or you can describe them here by using eta rho. So similarly, in this Schwarzschild metric, you can describe hyperbolas in this region, okay, using R and T, but here R will take values between 0 and 2gm, okay, and R is equal to 0 will really be the singularity. Okay, so that's why when in many textbooks you'll see them using the coordinates where R goes between 0 and 2gm as well. Okay, what that really means is that you're talking about a different coordinate patch, okay, which is not connected to the original coordinate patch, which is region 1. Um, yeah, so either you have to be using region 1, 2, 3, or 4, and you have to use the coordinates t, r, theta, phi. Okay. Now the interesting thing is, if you're using this tr coordinates, okay, so let me just draw that again. So this is your capital T, capital R, and this was r is equal to 2gm. Okay, and your hyperbolas here are parameterized by r is equal to constant. Okay, similarly your hyperbolas here are parameterized by r is equal to constant. But the interesting thing is, when you're in this region, partial r is a space-like vector. Okay, partial r is a space-like vector. You can see this easily because in the metric, the term which has partial t comes with a negative sign, partial r comes with a positive sign. Okay, but once I cross the black hole horizon into this region, on the black hole horizon, on the horizon itself, okay, partial r and partial t become null. Okay, that's what we understood as the light cones closing up. Okay, once I cross into region 2, which is over here, partial r becomes time-like. Okay, partial r actually becomes time-like. Okay, and partial t becomes space-like. Okay, so in region 2, if I'd written the metric using my t and r coordinates, what I would find is ds square is minus something times dr square plus something times dt square. Okay, so r would really become like your time-like coordinate. Now you see why it's inevitable that you go towards r is equal to 0, because you can not stop yourself from going towards r is equal to 0, because going towards r is equal to 0 is like going forwards in time. Okay, so you do hit the singularity eventually. Okay, there's no way to stop yourself from hitting that singularity, and in fact you can show that you will hit the singularity in finite proper time. So your roommate, if they have a clock with them, they don't have to wait an infinite amount of time. They will actually hit the singularity in finite amount of time. Okay, um, and in fact, if they struggle, okay, then they're basically not following a geodesic. If they're accelerating, they're not following a geodesic. So if they accelerate because of a rocket, so it's a non-gravitational force, they would basically not be following a geodesic. But we've seen that geodesics actually maximize the proper time that they take. So actually, if they're in free fall towards the center of the black hole, they would actually maximize the amount of time before they hit the singularity. So they extend their life before they actually hit the singularity by not actually trying to accelerate. The more you accelerate, the quicker you actually hit the singularity. Okay, so the big question is, what actually happens when you hit the singularity? Okay, crossing the event horizon is not special except for the fact that you can't come out. Okay, but the singularity is really special. The singularity means there's an infinite curvature of space-time. Okay, so we don't really know what happens there. Okay, your classical GR description in terms of this manifold breaks down. Okay, because if you're describing something which has an infinite curvature, okay, it's an infinite energy density. We don't really know what is going on there. Okay, in classical general relativity, you just say this is the end of where general relativity makes predictions. Okay, it's the end of space-time. Quantum mechanically, we expect that there's some inherent fuzziness, okay, in trying to measure a position very precisely and a momentum very precisely. Okay, there's some inherent fuzziness, okay, because of the uncertainty principle. So if you know the momentum of your roommate very well, you don't know their position very well, okay, and maybe they've not yet hit the horizon. So maybe this inherent fuzziness is going to create some fuzziness in the structure of the singularity. Okay, so maybe quantum mechanics somehow resolve the singularity. Okay, the singularity, by the way, exists both inside the white hole as well as in the black hole. Okay, there are two different singularities. The white hole singularity is from which we are born. The black hole singularity is the one in which you can die if you fall into a black hole. Okay. Yeah. Okay. All right. Okay. So I think this is a good point to stop, and let me just sort of sum up. Since this is the last class, okay, let me just sum up where we are and what we have learned. All right, so let's just backtrack a little bit. So what have we learned about general relativity? So we started by saying, let's just try to find a merger between the laws of special relativity, the framework of special relativity rather, and the law of gravity. Okay, so we've already seen this with the framework of special relativity incorporates a law of electromagnetism, Maxwell's equations plus the Lorentz force law, quite easily incorporated into the laws of special relativity. However, we saw that gravity is special. Okay, because of the equivalence principle, gravity, when you try to merge gravity with special relativity, Einstein realized that it actually leads to a deeper principle. And that deeper principle is the general coordinate invariance, not just invariance of the laws of physics under special transformations, which are Lorentz transformations, but quite generally under any arbitrary coordinate transformation, the laws of physics take the same form. Okay, so this is a new principle. And the second kind of interesting thing was that the metric of space-time, which is responsible for the gravitational forces that we feel, that is a dynamical quantity. That is something that has to be solved for by the motion of particles. Okay, so these are sort of the two principles that kind of underlie general relativity. One is that coordinate invariance it must be true for the laws of nature. It's a deeper principle than the laws of special relativity. And the metric is dynamical. Okay, so even though you started by thinking that, okay, maybe it's just a trivial thing to add a tensor and get and merge it with general relativity, with special relativity, you find a much deeper principle, okay, of general coordinate invariance. We've seen in the limit of weak gravitational fields, then it kind of leads to exactly the kind of merger that we were anticipating, of just some tensor added to special relativity, and you get some simple laws. But coordinate invariance is much more restrictive in terms of the full framework of general relativity. It leads to these complicated nonlinear differential equations, okay, in general relativity. Physical laws are now described by tensor equations on a manifold. And the tensor transformation laws are more general. Tensors are things defined on manifolds which don't depend on any coordinate system. Okay, they don't care about what coordinate system you use. But if you choose to describe them in one coordinate system, there's a dictionary which allows you to translate them to a different coordinate system. The components in one coordinate system can be transformed to a different coordinate system. And now you need to simultaneously solve not just for the trajectories of particles or for fields like electromagnetic fields, but you also need to simultaneously solve for the metric. Okay, particles influence the metric influences particles. Okay, and similarly, fields also influence the metric, and the metric also influences fields. Okay, like electromagnetic fields. Newtonian gravity emerges in the weak field limit. Okay, but we saw in the weak field limit you also get new predictions. You get predictions like gravitational lensing. The trajectory of light can bend in gravitational fields. You get the prediction of gravitational waves, something completely unique. Okay, and we're only starting to actually experimentally detect these features of general relativity. Okay, even though these predictions have been known for almost more than 100 years now. There are other effects like gravitational time dilation, gravitational redshift, okay, that we've seen in the linearized theory. And if you go to compact objects which are extremely dense, okay, where you pack them something with the mass of a sun into a region which is less than a Schwartzell radius, which is 3 kilometers, then you're in a strong gravity regime where you need to solve Einstein's equations exactly. Okay, and we've seen all kinds of exotic things come out when you solve Einstein's equations exactly. You get things like black holes, white holes, parallel universes, wormholes, all kinds of crazy things that you could not have anticipated before. Okay. And if you, one thing that we haven't touched upon in the course, okay, but I strongly encourage you to read about, is if you apply GR to the universe as a whole, you take everything in the universe and you see what happens to it, you will find that you get a solution with a metric which describes an expanding universe. Okay, and this was a prediction that was missed by Einstein, but was found by others. Okay, and later in the 1920s, it was actually discovered that the universe is expanding. Of course, today we know that the universe is not only expanding, but it's accelerating in its expansion. Okay, so this leads to the very rich field of cosmology, which over the last 30 years has really blossomed into a very precision science where we not only study this exact solution of an expanding universe, but we can also study the perturbations about this expanding universe. And these perturbations describe inhomogeneities in an otherwise smooth universe. On the very largest scales, the universe is extremely smooth. The galaxies are almost like a smooth fluid filling out the entire universe on very large distance scales, hundreds of millions of light years. Okay, but if you go to smaller scales, the universe is granular. You see regions where galaxies clump together, and other regions where there are very sparse galaxies called voids, okay, where there are almost no galaxies at all. And studying perturbations about this sort of homogeneous universe gives you a detailed prediction of the distribution of galaxies. Okay, and this underlies the study of cosmology. So GR is widely used in the study of compact objects in astrophysics, like if you want to study neutron stars, black holes, if you want to study gravitational waves emitted by the mergers of these exotic objects like black holes. And it's also used in the study of cosmology, which is the evolution of the universe as a whole. The only practical application so far of GR seems to be GPS, okay, but maybe someone will find more. Okay, so many things remain to be understood, particularly in the frontier of quantum gravity, okay, where the merger of quantum mechanics or quantum field theory and gravity. So I'll just list some of these problems. One is the black hole information paradox, which is what happens to information as it falls into a black hole. Classical GR says that nothing should come out. Quantum mechanically, Stephen Hawking showed in the 1970s that black holes actually radiate, okay, and they radiate thermal radiation. But that is a problem, because what it means is if you send a pure quantum mechanical state into a black hole and what comes out is thermal radiation, it means that you lost information about what that pure quantum mechanical state is. In quantum mechanics, time evolution is unitary, which means just letting particles do what they do means that you should conserve probability. That is, a pure state should remain a pure state. It should not become a mixed, what is called a mixed state. It should not evolve into something that is thermal. Okay, so basically there must be subtle correlations in the stuff that is coming out as Hawking radiation that somehow encodes what fell into the black hole. So maybe quantum mechanics resolves this puzzle of the singularity of the black hole, and maybe eventually the black hole does evaporate and releases back all the information that fell into it over very, 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 very long time scales. Okay, this is highly theoretical, unlikely to be observed, but is necessary for the consistency of quantum mechanics with general relativity. Another place where quantum mechanics and general relativity would come together is in trying to determine the initial conditions of the universe. Okay, what sets up the initial inhomogeneities in the distribution of galaxies? Okay, that grow into larger inhomogeneities. Okay, that structure of those inhomogeneities is set by some initial conditions. Those initial conditions, it turns out, are described by quantum fluctuations. Okay, in our best theory of something called inflation, quantum fluctuations actually describe, okay, so the entire universe, the galaxies, stars, us, all of us arose as quantum fluctuations in the very early universe. Okay, this is another very active area of study where we're trying to understand what is the source of those initial conditions, and can we test directly this theory of inflation that predicts, okay, those initial conditions. Another area of study that is huge, that is quite vast, is there seems to be a duality between theories of gravity, that is, theories described by general relativity or the quantum mechanics of general relativity, and what are called gauge theories, which describe other types of interactions like electromagnetic interactions or versions of the electromagnetic equations, which describe strong interactions and weak interactions, which operate at a subnuclear level. There seems to be a perfect duality, which means you can start with something that looks like general relativity, and you have an alternative description which looks nothing like general relativity, but rather looks like quantum field theory in Minkowski spacetime. Okay, and it's rather puzzling that these two are related, but there appears to be this dictionary that relates the two. Okay, that is, you can directly translate predictions in one description to predictions in another description. The weird thing is the gravitational theory is, let's say, a 4 plus 1D theory, whereas the gauge theory is a 3 plus 1D theory. That is, it lives in one fewer spatial dimensions. Okay, and so it's kind of like a hologram where the same information that you see in 5 dimensions is secretly encoded in 4 dimensions. Okay, and this idea has been called the holographic principle. It's like a hologram where you encode 3D information on a 2D surface. Okay, similarly, this is the universe as a whole. A gravitational theory which describes the universe, a 4 plus 1D universe, can secretly be described in one lower dimension. How is this encoding happening, right, is something that people are trying to understand. Okay, this is called the ADS-CFT correspondence or holographic duality. And another area of active research, again, which is inspired by a quantum theory of gravity, is extensions of general relativity, which basically we wrote down the simplest possible equations of general relativity. But general quantum theories predict that these equations should have corrections which are, let's say, higher derivatives. Okay, so our theory of the Einstein tensor is equal to the stress energy tensor. This was second order in metric derivatives. It was non-linear, but second order in derivatives. But maybe you have higher order derivative corrections. Okay, and maybe those can become important. Okay, at some short distance scales called the Planck scale. Okay, which is a scale of 10 to the minus 33 centimeter. It's a scale formed out of the constants h bar, c, and Newton's constant. You can get only one dimensionful quantity which has dimensions of length, and it has a length scale of 10 to the minus 33 centimeters. So if I want to describe space-time on these very short distances, we need some kind of quantum theory of gravity to describe it. Okay, one candidate for such a quantum theory of gravity is string theory. Okay, and which is a rather beautiful theory, which says that really fundamentally all particles that we see are essentially made up of tiny vibrating strings. Okay, so gravitons, which are the tiniest quantum that make up gravitational waves, are made up of one particular vibration mode of these strings. Okay, really behaves like gravitons. Okay, which are like photons make up electromagnetic waves, gravitons make up gravitational waves. So string theory is sort of one candidate for a quantum theory of gravity. And indeed, many of these ideas, like extensions of GR, duality between gravity and gauge theories, many of these ideas are sort of realized in string theory, which is why string theory, even if it's not the right theory of quantum gravity, certainly seems to lead us to a lot of rich ideas about what the quantum theory of gravity should be, okay, or what properties the quantum theory of gravity should have. Okay, so yeah, so unfortunately we're out of time. I mean, there's a lot more that you can explore if you want to study general relativity, a lot of different directions to go in. Okay, so I hope that this course was kind of a gateway for you to kind of explore these different directions, whatever your interests are. Okay, okay, so with that we'll end. We can take a few questions, but we'll stop here. Yeah. Sorry, can you pull down your mask now? They could exist. So in a sense, so when you study cosmology, one possibility is that, so the universe is so the so-called Big Bang cosmology, the universe is from a singularity very similar to the white hole singularity. Everything comes out from the singularity. So you can't say what happens at the singularity, but any moment after the singularity you can talk about. You would never be able to observe it today, but you can extrapolate its existence from what we see today. Yeah, so you can, okay, so you can of course write down a gravitational theory. We are not talking about a full 5D space, because it would be sort of how you project a full 5-dimensional space onto a 4-dimensional space. Okay, so it's the boundary of this 5-dimensional space is a 4-dimensional space, and that 4-dimensional space. So basically, this is called a bulk, and this is called a boundary. So basically, the bulk is related to the boundary. So yeah, so very similar to like if you have the interior of a sphere, right? It can be projected onto the boundary. Okay. But the interesting thing is, when you calculate for, and it's very closely related to the black hole information paradox, in that one of the things that Hawking showed is that the entropy of a black hole actually scales like its surface area, not like its volume. And normally in thermodynamics, we think about entropy as scaling like volume. And that really is from a microscopic description. We expect that basically every volume can hold some piece of information. Okay, but somehow what we're saying is that really all the information that you can store in this room can really be encoded on just the boundary of this room. And that is quite a surprising fact. these theories seem to indicate that it is. These theories, whether they're true or not, the direct test we can't do. But the consistency of quantum mechanics with GR seems to require it. Well, no, it's really more subtle than that. It's sort of the, like, you think that you have a lot of degrees of freedom in 3 dimensions, but secretly there are restrictions on those degrees of freedom, which ensure that they can be encoded on a 2-dimensional surface or one lower dimensional surface. So that's the real reason. It's not. I mean, of course, if you had your full degrees of freedom, they can't be encoded in 2 dimensions. Okay, let's stop here. Thank you.
Thank you.